All right, this has the potential to be a really long video, but hang in there. There's a lot of information about atomic structure and electron configuration. This is AP topic 1.5, so let's start off by talking about subatomic particles. You might remember from Chem 1 that there are protons, neutrons, and electrons in the atom. Protons and neutrons are found inside the nucleus, and because protons are positive and neutrons are neutral, the nucleus overall has a positive charge, which is going to be important as we move forward. Electrons are found outside the nucleus, organized in the electron cloud, which we'll talk about more in just a second. And a special term for electrons are valence electrons, which are electrons in the outermost shell. And we call that shell the valence shell. So now let's get into talking more about the electron cloud structure. So the electron cloud is organized into layers that we call shells or energy levels. And those layers are numbered 1, 2, 3, 4. That corresponds to the row of the periodic table, which we'll look at more in just a second. Within the energy levels, or the shells, you have subshells. These are lettered S, P, D, and F, and that corresponds to the block of the periodic table, which again we'll talk about in just a minute. Within your subshells, you have a certain number of orbitals, and then each orbital can hold up to 2 electrons per orbital. So let me show you what this looks like in terms of energy. So in the first energy level, which is the one that will be closest to the nucleus, you've got one subshell that contains 1 orbital. That is the S. So this is the 1s. In the second energy level, you also have an S, which would be the 2s. And then we add in the P subshell, which has 3 orbitals. So altogether, these 3 orbitals make up the P subshell. In the third energy level, you have the 3s, the 3p, and then we add in your 3d. Now, you might notice in my energy diagram here that the 4s is actually slightly lower in energy than your 3D. And that's going to be important when we look at it on the periodic table in just a minute. Okay, and then this pattern continues. So in the fourth energy level, we have the 4s, the 4p, the 4d, and we add in the 4f. Unlikely you're going to have to do much with that in AP chemistry, but it is. Now let's talk about Coulombs Law. So this is the form of Coulombs Law that you're going to see on the AP chemistry exam equation sheet. So I want to point out something to you. First of all, you will not have to do any calculations with Coulombs Law on the AP exam. It is just there for you to use for qualitative reasoning, okay? You do not have to quantitatively apply it. But what you need to know is that Q1 and Q2 are charges here, and R2 is the separation between the 2 charges. Now, it's important for you to remember with Coulombs Law that opposite charges attract and similar charges repel. So this force could be attractive if they're opposite charges, or it could be repulsive if they're the same. So let's talk about how to impact that attractive or repulsive force. So that force would increase if we increase the charge magnitude, right? Because that would increase the magnitude of your numerator. Or if we decrease the distance between those charges, because that would change your denominator here. That would make this smaller, and therefore this whole term would get larger. Or we can do the opposite. If we want to decrease these attractive or repulsive forces, then you can decrease your charge magnitude, or you can increase the distance between those charges. So why do we care about Coulombs Law? Well, we care about Coulombs Law because it matters when we're writing electron configurations. So let me show you a periodic table that I've labeled here. So if you remember, I told you that the energy levels correspond to the rows of the periodic table. The blocks of the periodic table correspond to the sublevels. Okay, so the periodic table can be seen as a map of electrons. If you want to think about each element as corresponding to 1 additional electron being added. So then we can use the periodic table to help us figure out how to write our electron configuration. So I'm going to show you 2. So I'm going to show you magnesium, which is here in green, and antimony, which is here in pink. Okay, so for magnesium, we're always going to start in your 1s. So 1s, 1, 2, because this single block over here is actually in the 1s, 2s, 1, 2, 2p, 1, 2, 3, 4, 5, 6, 3s, 1, 2. And then you're going to land on the element that you're describing. So here we go. So you've got 1s2, 2s2, 2p6, 3s2. So if the periodic table is a map, the electron configuration is like directions. And then just like with directions, we can use a shortcut. So we can use the noble gas for the end of the row above the element. So for magnesium, that would be neon. And then just include what's on the same row as the element itself, which is 3s2. Now antimony is a little bit longer. It's all the way over here. Now this allows us to point out some features. Okay, so part of this is going to be the same as what we just did for magnesium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we hit the D. So if you remember what I told you, the D is actually higher in energy than the S. And so this is actually the 3D. So for your whole D block, you're going to take 1 off the row number, okay? So this would be 3D10, 4p6, 5s2, 4d10, and then back to the P, 5p, 1, 2, 3. So we can see that written out here. And then again, you can also use your noble gas abbreviation, which for antimony is krypton, 5s2, 4d10, 5p3. So this notation is really useful if you're trying to identify valence electrons because bam, there they are. Easy to see. Now, sometimes you're asked about unpaired electrons. So remember that an orbital can hold at most 2 electrons. And remember as well that electrons repel each other, right? So they're going to spread out as far as they can, which means they're not going to have a roommate until they have to. So that's that electron-electron repulsion situation there, okay? So what that means is here we've got 1 electron in an orbital, 1 electron in a different orbital, 1 electron in a third orbital. We don't pair up until we get here. So now we've got 1 paired and 2 unpaired. Here we've got 2 paired and 1 unpaired. And then here we've got 3 pairs, okay? And so you can kind of count all the way across. So like 1, 2, 3, 4, 5 unpaired, and then in reverse, 4, 3, 2, 1, 0 unpaired. And so you only have 0 unpaired electrons when you get to the end of your sublevel blocks. By the way, if you ever have to do an F, that is 2 rows off. So D is when you're looking at your energy level. So let's look at the 6th row here. 6s, 5d, 4f. Okay, one more thing to talk about, and that's the electron structure and ions. So we're going to talk about 2 kinds of ions. When you're forming positive ions, electrons are lost, right? So electrons are lost from the valence shell first and then from the d subshell if necessary. Now we really only see them lost from the d subshell when we're talking about transition metals. So let's look at gallium here. So here's gallium's electron configuration. Gallium takes a +3 charge, which we can tell based on the column. And so it loses these 3 valence electrons, and then that's it. This is electron configuration for Ga3+. Now with negative ions, I think it's actually a little bit easier because negative ions add electrons and they're going to go into the valence shell as well. And generally they fill the p subshell, whichever the last one is. And that's generally how negative ions are formed. So there you go. Atomic structure and electron configuration. And I'll see you again soon for topic 1.6.